All right, here we are finishing up with the examples for exponential and logarithmic derivatives. And we're going to jump in right to the deep end. So here we see we have two functions. We have 2x cubed, so we have a polynomial multiplying a natural exponential function. It means we're going to have to use product rule. So f prime, so the derivative will be derivative of the first function. So that is the 6x squared multiplied by the second function, plus, using our product rule, first function multiplied by the derivative of the second function. So the derivative of e to the x is itself multiplied by the derivative of the exponent. And that's where we'd leave it. You can do some simplification if it needs it, but in terms of what I'm testing, this is as far as you'd go. All right, next one. This is a straight exponential function. The nice thing, or the most enjoyable thing here, is that we have a trig function involved in there. So that makes things just that much more exciting. So what's the derivative? Well, using your chain rule, if you want to think of it that way, we need to take the derivative of the e function first. So the derivative of the e function is itself, e to the exponent sine x, multiplied by the derivative of its exponent. So if you're thinking about it in terms of chain rule, we took the derivative of e. Now we take the derivative of the exponent, and that would be sine x. So the derivative would be cos x. Now, be careful with this trig function. You now have to take the derivative of the angle. So then you'd have a 1. So the derivative of that original function is that right there. So e to the exponent sine x is e to the sine x cos x times 1. All right, so there's our first pair of examples. What happens if we have quotient rule? Not a whole lot changes, except we now have new rules for dealing with derivatives of exponentials. So h prime of x, quotient rule says take the derivative of the numerator. So we would have 3x squared multiplied by denominator minus numerator, and the derivative of the denominator is itself multiplied by the derivative of its exponent, which would be 3. That's all divided by our denominator squared. So e to the 3x squared. And again, that's where you can leave it for this particular unit, because all I'm testing is, can you apply your skills of derivatives? I'm not looking at, do you have the algebra skills to simplify that? All right, I'm assuming you do have the algebra skills, and we're going to find out in the next unit when there's more application questions with that. All right, example 4. Once you see x's and y's all mixed into an equation, you need to understand that it's implicit differentiation. So carefully picking this apart, there's two functions here, so that means I'm going to have to use product rule. For the second one, it's only an exponential, but I'm going to have to use the product rule in the numerator, and then just a straight power rule there. So starting off, we said already this is going to be a power rule. So the derivative would be the derivative of the first function, which would be 2, multiplied by the second function, plus the first function multiplied by the derivative of the second. The derivative of e to the y is itself multiplied by the derivative of the exponent, which would be 1, and I'll use y prime in this case. All right, so there is the derivative of just the first term, plus a derivative of e to the exponent xy. So the derivative would be the derivative of itself, the derivative would be itself multiplied by the derivative of the exponent. That exponent is a power rule. So that means it would be derivative of the first term is a 1 multiplied by y plus the first term multiplied by the derivative of y is 1 y prime. And there we go. And that's all going to equal 2y. We got to take that derivative yet. Oops, I just want to shrink it down a little bit to get some space. So there we go. And the derivative of 2y would be 2y prime. Okay. Now here's an example where we can go ahead and we can simplify it for y prime. But at this point in time, and you can ask on a test, I'm probably only going to want that first or initial step, that initial phase there. All right. But you can go through and isolate for y prime as you have before. All right. Last two examples that I want to look at today. Really just looking at how to take the derivative of a logarithm. So the derivative of a logarithm, we said earlier, is the, you take 1 over whatever the argument was, or what you're taking the log of. Sorry, I got to point to it for you. 1 over the arguments. The argument's in there. So in the denominator, I will have x cubed minus 6, and then you multiply by ln b. So the ln of the base, here it's going to be ln 10. If there's no base indicated, it's base 10, so it's ln 10. And then we have to multiply this fraction by the derivative of what's inside the argument there. So we'd end up with 3x squared. Now I'm going to take it one step further just to put it all together. So the end result would be 3x squared on top, and it's being divided by ln 10 x cubed minus 6. All right, so there we go. And yeah, you can leave it in that first line. I just wanted to show that the derivative of the argument does end up in the numerator. Number 6, the derivative here. First thing I'm going to do, I'm going to rewrite this to get rid of the radical sign. So the ln of 4 minus x squared to the 1/2. Okay. So when you go to take the derivative of that, so m prime of x would equal 1 over the argument. So that would be 4 minus x squared to the 1/2. And then we take the derivative of that argument inside the brackets there. Sorry, people knocking at the door. So 1 over the argument. So the argument again is what's inside the brackets when you're taking the log or logarithm. So that's my argument. So now I got to take the derivative of that argument. So the derivative then, and I'm going to put it in square brackets, the 1/2 we go up front, and we're going to have to use chain rule, minus 4x squared to the negative 1/2, multiplied by what's inside, which is negative 2x. Now, for argument's sake, I'm going to simplify this just a little bit to show you what it turns out to be. So inside the last set of brackets here, this 1/2 and that 2 are going to cancel out. Because that 4 minus x squared is the negative 1/2, it would move to the denominator. So maybe I'll show an extra couple steps here just so you can follow the algebra. But what you find is sometimes these logarithmic functions actually work out not too bad. So we have negative x left, and then this would be 4 minus x squared to the positive 1/2, because now it's in the denominator. And now, when you multiply these fractions together, the square root, or the 1/2, would disappear, so you just have 4 minus x squared in the denominator and negative x on top. So it's actually what the derivative reduces to. No logarithms, no exponential. So you think it's going to be worse than it really is. All right. Last example. Determine the equation of a tangent line to that function at the point 1, 0. So it's the same process we've been talking about all along. And these questions, if you look back in the homework, these questions are quite repetitive. It's just the function has changed. So, oops, not Lx, ln of x to the exponent 1/3, taking the derivative, f prime of x, we would have 1 over the argument multiplied by the derivative of the argument. It's just a power rule. So 1/3 x to the negative 2/3. Then you can simplify this before you do the substitution, and I think I will. So when I do this cleaning this up, I'm going to leave the first fraction alone. And the only thing I really do in the second fraction is get rid of that negative exponent. So it turns out the 3 goes into the denominator, as does x to the 2/3. Now when you do this, you're multiplying fractions, you multiply the top, or the numerators and the denominators together. So you end up with 1 over 3, and x to the 1/3 times x to the 2/3. Your exponent rules say you add your exponents, so you end up with just 1 over 3x. So that is the derivative for our original function. So moving back over here, what's the slope? The slope at the point is 1, 0. So f prime of 1. So we're looking for the slope at x equal to 1. It'd be 1 over 3 times 1, so it'd be 1/3. So there is the slope. Using our equation of a line, we have our x and y value, so we can just plug it in. So x minus 1 plus 0. So we end up with 1/3 x minus 1. So there is your slope of the tangent, right there. All right. If you have any questions with this, please make sure you seek me out. There is quite a few questions here to work through, but it's important that you're comfortable taking those derivatives because it is going to pop up, and so you want to make sure they're clearly done on your cheat sheet. You want to know how to use them, and you want to know how to use them properly. So if you have any questions, make sure you ask or note them right now, and then you can ask them tomorrow.